Hey guys, this is Mrs. Bradfield, and it is Wednesday, March 18th, and we're going to finish up these 2-5 parametric notes. We're going to do some more graphing of parametric equations, and we're going to solve problems related to the motion of projectiles. So, exactly what it sounds like, rockets, anything we're shooting, should be shooting a basketball, hitting a ball, anything that's going forward or going away from us. There are many restrictions. There may be restrictions on the domain of a graph when parametric equations are converted to rectangular equations. So I just was testing my pen there. Anyway, so sometimes when we graph these equations, there's a possibility that we're going to have some restrictions on our domain. So some places where there might be an asymptote or a hole or an endpoint or some kind of restriction. So in this first part, in example 1, it says, write x equals 1 over the square root of t and y equals t plus 1 over t in rectangular form. So we're going to start doing that. And remember that what we want to do is I'm just going to take each one and I'm going to solve for t and then set them equal to each other. So in the first equation, I'm going to multiply by square root of t. And then square root of t equals 1 over x. And we'll square both sides. And I get t equals 1 over x squared. Okay, and then on the other equation, I am going to multiply both sides by t, so I'm going to get ty equals t plus 1. We're going to subtract t, get those on the same side, and then I'm going to factor out a t. So that t is equal to 1 over y minus 1. Okay, and then we set them equal to each other. So let's see, I have 1 over x squared equals 1 over y minus 1. If we just do a little cross multiplying, we'll get y minus 1 equals x squared, or y equals x squared plus 1. Okay, so this is our equation in rectangular form. So what kind of restrictions are we looking at? Well, you can see that really in y equals x squared plus 1, the x could be all real numbers. There aren't any restrictions on what x can be there. But if I look at what x was originally equal to 1 over the square root of t. So things that are going to happen there, first of all, I can't take the square root of a negative. So t would have to be greater than or equal to 0. But then also, if it were equal to 0, that would cause me to have a denominator that's 0, which, of course, dividing by 0 is undefined. So 0 can't be an option, which means that t would have to be greater than 0. And that would result in x also being greater than 0. And so that's the restriction on the x value. And then so when we go to graph this, we have, it's a parabola. And so if we were to rewrite it, I would say that this is x squared equals y minus 1. And so we have an ordered pair that is, or sorry, a vertex that is 0, 1, and the axis of symmetry is x equals 0. So I'm going to go ahead and graph that on there, 0, 1. And we know that's our axis of symmetry, and it should open up. And then we just need to get at least another point, and I'm going to let x, I'll let x equal 3, in which case if x is 3, we would have 9 equals y minus 1, so y would equal 10. So I would also have a point at 3, 10. And then one on the other side because the y-axis is actually our axis of symmetry. So as it is, it looks like this is our graph because it's a parabola. And if I could have done a little bit better job. But we want to get rid of part of that because it says that x has to be greater than 0. So I'm going to erase some of this. I was hoping to erase a little less, but that's okay. And I'll just go back so that if x has to be greater than 0, I would have an open dot here and then the rest of my graph. So that's what would happen. Okay, in the next one, we'll look at the same thing here. So I want to write them in rectangular form. So I have x equals the square root of t plus 4 and y equals 1 over t. And I'm going to solve for t. So I'm going to square both sides on this one for the x equation, which is x squared equals t plus 4. So t is equal to x squared minus 4. And then for the y equation, we can just switch those places and we get t is equal to 1 over y. Okay, and then when we set them equal to each other, x squared minus 4 equals 1 over y. And so that equation would be y equals 1 over x squared minus 4. Okay, so now we look at the restrictions there. For the graph that we do have, or the equation that we do have on the rectangular form, I know that my denominator cannot equal 0. So I know that x squared minus 4 cannot equal 0, which would mean that x squared cannot equal 4, and so x cannot equal plus or minus 2. So that's one restriction, but then the other restriction that we have to look at is the one that defined x to begin with. And in this case, when we take the square root of something, first of all, under the radical, you can't take the square root of a negative. So t plus 4 has to be greater than or equal to 0. And so t is greater than or equal to negative 4. Well, if t is negative 4, anyway, if t is negative 4, that would give us 0. So we can take the square root of 0, which is 0. And then anything larger than that would be positive. So that tells me that x is going to be greater than or equal to 0, given that t is greater than or equal to negative 4. Okay, now we have to kind of look at how these two are working together. I know that x has to be greater than or equal to 0, but I also see that x cannot equal negative 2 or positive 2. Well, x is automatically not negative 2 if it has to be greater than or equal to 0. But we also have to then add the fact that it can't be 2. So we say x cannot equal 0, or is greater than equal to 0, and x cannot equal 2. And then I'm not going to go ahead and graph that, but what we would do is on our graph, we would have a closed dot at 0, and then there would be a hole at 2. There would be a hole at 2 when you went to graph the equation. It actually, well, let me go ahead and do it. It actually looks like this. We've got a vertical asymptote at x equals 2. We actually have multiple ones if we were to graph this, but this is the main one here. And because we know it can't equal 2. And then we also know that we would have a horizontal asymptote that is the x-axis, because the coefficients of the top and the bottom, well, actually it's because the coefficient of the top is less than the coefficient of the bottom. It ends up looking like this. And I want to say maybe something like that. Okay, I'm going to back that up just a little bit. Get rid of that last mark that I made, and it should look like, sorry, it should look like this. So that's what our graph would look like. So you can see that we would have a dot here at 0, and then we have that asymptote of 2. All right, for the next problem, it says use each parameter to write the parametric equations that represent y equals x squared minus 4, given that t equals x. And so we already have that y equals x squared minus 4. And we want to write it in parametric terms given this. So if t is equal to x, then x is equal to t, obviously. So there's my x equation. Now I want to write a y equation with a t in it. Well, if x is equal to t, all I have to do is replace the x and the x squared minus 4 with the t. And there is my, my set of parametric equations. And then I'm going to do a little graphing. So I've got a t, an x, and a y. And I'm just going to kind of pick some positives and negatives. Let's say I'm doing -3, -1, 0, 1, and 3. And so obviously all of my x's are the same as my t's, so I can fill that in. And then to do my y's, that's -3 squared is 9, minus 4 is 5. -1 squared is 1, minus 4 is -3. 0 minus 4 is -4. 1 squared is 1, minus 4 is -3. And 3 squared is 9, minus 4 is 5. And so I've got my points that I can graph. I have, and so keep in mind that these are my points right here, not the t, but as I graph it, I'm going to write those down.